Hello. Hope everyone's doing well. A couple more people in here. Okay, so last class we started thermochemistry. We went over what work and heat are, potential energy and kinetic energy, how to calculate kinetic energy, the units for energy, what internal energy is, or that delta E. You want to know what happens to that internal energy when you're dealing with things where you have endothermic reactions versus exothermic reactions. So is delta E positive? Is it negative? We know that delta E is equal to the heat plus the work of a system. So those were those kind of simple problems of like, calculate delta E if we know how much heat is absorbed and how much work was done. So you want to be able to calculate some of those. And we're going to move on to enthalpy. All right. So if a process takes place at a constant pressure, and that's usually what we're dealing with in most of the situations, and the only work done is this pressure volume work, we can account for heat flow during the process by measuring the enthalpy of the system. And so heat, our enthalpy is our heat gained or lost by the system. And then we will add, so we've got our enthalpy, it's going to be equal to our internal energy plus the change in pressure over volume. But again, a lot of times we're dealing with constant pressure, so we can almost ignore this and just deal with delta H, or our enthalpy equaling our change in internal energy. I'm not going to have you guys actually running any problems with this equation. So just know that for this equation, for enthalpy, you don't need to calculate. Okay, so make a note somewhere that says you don't need to stress about running through calculations with that. And then if we were to delta this, so the change in enthalpy is equal to, or the change in our heat of reaction is equal to the change in parentheses, this again, this E, which is our internal energy plus the pressure times the volume. And again, we won't be running any calculations with this equation. And you can see it written in this way as well. And then they do some algebra trickery here. So we know if delta E is equal to Q plus W, and W, which we have here, is equal to negative P times the change in volume, we can substitute these into the enthalpy expression. So we can take, we've got our delta E, and if you see that right there, that would sit in here. These two are the same things, right? So it would end up being delta H equals Q plus W, and we know W is the opposite of this. So those two things end up canceling. And so we end up getting that delta H will actually equal Q. So at a constant pressure, the change in enthalpy is just considered the heat gained or lost. So this is really the main concept that we want to have. And again, we're dealing with most situations being constant pressure. So our delta H of reaction is just talking about how much heat did the environment gain or how much heat did the environment lose to the system. And so we would consider a process to be endothermic if delta H is a positive number, because again, delta H, looking back at the last slide, delta H is the same thing as Q, and Q is our heat. So if delta H is positive, it means our Q is going up, which means our heat is going up, or we're absorbing heat. It's important to know the signs on those and how they relate to endo and exothermic. Obviously, the opposite is true for exothermic. So if we have heat leaving the system and going into the surroundings, we'll say that our delta H is negative. So positive values of delta H or heat of reaction are going to be an endothermic. Negative values will be an exothermic reaction. Just sort of intuitive with what we've been talking about with systems and surroundings. So just so you know, a chemical bond, so if we've got two things that are bonded together, there is a sort of a net attraction or force between the nucleus and the electrons. So if I want to break this bond, say I want to cut this thing open or separate these two things, I have to put a certain amount of energy, or it needs energy in order to break this bond. Because I want to separate this sort of positive and negatively charged thing. So breaking bonds requires energy. If breaking bonds requires energy, the opposite is then true about making chemical bonds. If I make a chemical bond, I'm going to release energy. So if I've got, let's say I've got oxygen over here on one side and nitrogen over here on the other side, and I'm going to bond the oxygen and nitrogen together. When those two things bond with each other, they're going to release energy into the system. So we can think of breaking bonds. Here they require energy, and then making bonds releases energy. And then the potential energy that resides in chemical bonds is known as chemical energy. So we talked about how there was potential energy is based off of a material's position or based off of its chemical composition. Well, when something has chemical bonds, because when we break those bonds, they produce energy, those chemical bonds are actually like a stored source of energy. We call it chemical energy. When we're dealing with a chemical reaction, we generally are making and breaking bonds. If there is any heat gained or lost, or any energy gained or lost in a chemical reaction, it usually comes out in the form of heat. Sometimes we do see a change in energy with the release of, say, something like light. Like when we burn magnesium, for instance, it glows really bright, but a lot of times it'll be heat that we see. So any reaction where we're producing heat is exothermic, right? The surrounding environment is going to get warmer. Any reaction that consumes energy will be endothermic. So if it feels cold to your hand, and it's not because you put it in the fridge, you just happen to mix two room temperature things together and they start getting cold, we're going to say that's endothermic because it's pulling heat from your hand. So the change in enthalpy or change in delta H will always be this formula, products minus reactants, okay? So delta H is always going to equal the enthalpy of your products minus your reactants. And we will come back to that, but this is an equation that gets used quite often in chemistry in a bunch of different ways, not even in just reference to delta H, but other things where we get this idea of like products minus reactants, products minus reactants. So if we look at this over here, let's say we have, if we know our delta H of our products and we know the delta H of our reactants, we can separate, subtract the two to get our delta H or our change in reaction. And then when we're finding the delta H, it's sometimes called the enthalpy of reaction or the heat of reaction. And again, that delta H, positive being endothermic, negative being exothermic. So there's a couple of things about enthalpy that you want to know. One thing, enthalpy is an extensive property. And so what that means, enthalpy is an extensive property, is that it depends on the amount of material that you have. So if I've only got like a little bit of gasoline, the enthalpy that it contains is not going to be a whole lot. If I have, let's say, a truck full of gasoline, I'm going to have a lot of enthalpy in that truck. So the more material you have, the more enthalpy you can have. Doesn't say it on these slides, but enthalpy is also a state function. So just note that enthalpy, it doesn't matter how you get to that delta H, what path you've taken. The only thing that matters is the current state that it's in. Delta H for a reaction in the forward direction is going to be equal in size but opposite in size in sign as the delta H for the reverse reaction. So we could see that on the previous slide here. So if I'm, let's say that I'm taking this CO2 and H2O, let's go in the other direction. So let's say we've got methane and we're going to combust it with oxygen. So I'm going to combust this to produce CO2 and H2O. I am going to release heat. This will be my change in delta H of negative 890 kilojoules. So that's how much energy gets released every time I run through this, this chemical formula once. If I instead was to take the CO2 and the H2O and somehow combine it in a way where I get CH4, our methane, and our O2, our oxygen, so we do the reverse reaction, it will have the same delta H number, but the magnitude is, or the sign is opposite. So here it's releasing minus 890 kilojoules. Here it's absorbing 890 kilojoules. So equal and opposite. And then the final thing there, that delta H for a reaction depends on the state of the products and the state of the reactants. And when I say state of products and reactants, I mean if it's a solid, a liquid, or a gas. If we have something that is in a gaseous state, delta H will end up being bigger. So we do want to take those into account. Okay, so calorimetry, we can't measure enthalpy or the change in enthalpy directly of our reactants and products. We can only measure it through, we can't say, hey, the reactant has this much energy and the product has this much energy. We can only see the difference in the products and the reactants. And the way we would do that is by using a calorimeter, which is really just a fancy word of saying, like, I have a styrofoam cup, and I have a bunch of water in there, and I stick whatever sample, let's say it's a, I don't know, let's say that this is a piece of food or something, a carrot. And what I do is I light the carrot or I combust it, and the carrot will change into its products and it will release a certain amount of energy. I can't measure its energy directly here, but I can measure it because the temperature of the water will change. So if it's releasing a little bit of energy, the water temperature will increase slightly. If it's releasing a lot of energy, let's say we've got like 65 carats in there, the water's temperature should increase drastically. So we sort of indirectly, through the change in temperature of water, are able to figure out the change in delta H of the material that we were looking at. And that's what we do with the calorimeter. So before we can get into how to use a calorimeter, I mean, we're not going to be actually using a calorimeter, but you'll be doing calculations with the calorimeter. We have to talk about heat capacity and specific heat. So the amount of energy required to raise the temperature of a substance by 1 degree Celsius is known as its heat capacity. So if I want to take a piece of gold and raise it from 55 degrees Celsius to 56 degrees Celsius, there's a specific amount of energy needed in order to do that. And that specific amount of energy will be different than other substances. We spend a lot more time using what's known as the specific heat capacity, which is different than the heat capacity. Specific heat capacity is the amount of energy required to raise the temperature of specifically 1 gram of the substance 1 degree Celsius. So if I have 1 gram of gold and I want to raise it 1 degree Celsius, there will be a very specific number for that. For water, for instance, if I want to raise 1 gram of water 1 degree Celsius, I would have to use 4.184 joules of energy in order to do that, or its specific heat would be 4.184 joules per gram degree Celsius. So it's got funky units. So specific heat is equal to the heat transferred divided by its mass times its change in temperature. And this isn't usually how we see it written. If you've taken chem recently, you may see it written like with these two variables put in different places. Okay, but it's Q equals MCAT, or Q equals MC delta T. Q equals M times C times delta T. Now, the way they have it isolated here is they isolated for specific heat, which is C. And so in that case, C is equal to Q, which is our heat, over the mass times the change in temperature. Both the mass and the change in temperature are underneath the fraction bar in this case. Now the units of Q are joules, the units of mass are grams, and the units of temperature are degrees Celsius. So this is the unit for specific heat. It's a funky unit. Sometimes it's also written as calorie per gram degree Celsius if we're using calories instead of joules. And sometimes you will see it as joules per gram Kelvin as well. That one's not quite as common. So Q equals MC times delta T. And there's a couple more slides here where we can go a little bit more into detail. Okay, so there's our Q equals MCAT. Here's the specific heat or our C value for a couple of different objects. You do want to know water's specific heat off the top of your head because we're going to use that like all the time. So it's 4.18, or sometimes people will write it as, I usually use 4.184, put a 4 at the end. And again, the units on the specific heat are joules per gram degree Celsius. So if you look at this, water actually has a very, very high heat capacity, much higher than silver, gold, or copper. So what that says is that in order to raise 1 gram of water 1 degree Celsius, I need 4.184 joules. In order to raise 1 gram of silver 1 degree Celsius, I only need 0.235 joules. So it actually takes more energy to raise water up 1 degree Celsius than it does any of these metals. And if you don't believe me, well, think about when you're heating up a tea kettle filled with water. How quickly does the metal tea kettle get hot? Pretty quickly, it will heat up. How long does it take for the water to get hot? It's like never fast enough. So the water is just going to take a substantial amount of energy to increase its temperature. One thing I'm going to show you for Q equals MCAT, just because I know sometimes people have trouble isolating variables.
I ask a question?
Yeah, what's up?
So why is it to the -1? All those.
Why are all those values to the -1?
Yeah.
Because here you're talking about -1 is another way of saying that it's below the fraction bar.
Okay.
Okay, so for this thing right here, another way to write that is joules, gram, degree, Celsius. You put those two underneath a fraction bar when it's -1.
That makes more sense. Thank you.
So we've got Q equals MCAT. Sometimes Q is lowercase, sometimes it's uppercase. You see it in different ways. Q equals MC delta T. Okay, if, for isolating variables, you can make a triangle like this. And then we're gonna divide it into 4 sections. On the top, we'll put the Q, and on the bottom, we'll put the MCAT. So think of this bar here is a division bar, this one right here. And then these two are multiplier bars. So if I want to solve for Q, I take mass times C times delta T. That's what we have here. Let's say that I wanted to solve for mass. Mass is going to be equal to, Q will be on the top. This is a divider bar, a fraction bar, and then C and delta T will be underneath it. Delta T will be underneath it. Okay. If I want to solve for delta T, all right, delta T is going to equal, my Q goes on the top, and then my mass and my C are on the bottom. Mass and C on the bottom. Okay, so that's a quick way to figure out how to isolate variables if you're having trouble with that. Back over to our slides here. So again, if we've got, if we have a constant pressure, we can carry out a reaction in an aqueous solution, aqueous meaning water, and use just a simple, really a styrofoam cup or 2 styrofoam cups. And we can indirectly measure the change in heat by measuring the change in water. So let's say I was to throw a piece of hot metal in here, and the water's temperature increased by 35 degrees Celsius. Well, I could figure out how much energy the metal lost because I know how much energy the water gained. It should be equal and opposite to each other. We're assuming that this is a closed system. So because the specific heat of water is well known, and it will be well known for you, 4.184, we can figure out our delta H for the reaction using this equation. So let's try, we'll try this simple one here. The temperature of 251 grams of water is changed from 25 degrees to 30 degrees Celsius. How much heat was transferred to the water? So anytime you're seeing change in temperature, heat capacity stuff, you're going to want to use the Q equals MCAT equation. Now in this case, it says how much heat. So Q is heat. This is really common. I see people get Q and C mixed up. Q is heat. C is specific heat capacity. C is a value that you can get off an appendix. It's always going to be the same value for the material. So if we're talking about gold, the specific heat is consistent. If we're talking about water, which is usually the case, it will always be this 4.184 joules per gram degree Celsius. So if we want to figure out Q, all we're going to do is take the mass of the water, which is a value of grams. So make sure your mass is in grams. Make sure your C is in joules per gram degree Celsius. And then make sure your change in temperature is T final minus T initial, okay? I don't think I said that earlier. And this will be in units of delta C, or degrees C. So we have our mass, which is 251 grams. We've got our specific heat capacity of water, which is always 4.18 or 4.184 joules per gram degree Celsius. And then we multiply that by delta T. Delta T will be final temperature minus your initial temperature. So in this case, 30 minus 25 will be 5.0. What you can see is that gram and gram unit will cancel. Celsius and Celsius unit will cancel, and you'll be left with just units of joules, which is what we want because we're talking about Q, or energy. So we end up with 5,250 joules, or 5.25 kilojoules. They just moved the decimal over 3 places. So this value for Q was a positive value. Right? We didn't end up with a negative number, so it means that the water absorbed that heat. Positive means it's taking that heat on. Negative would be giving the heat off. So let's do another problem just using specific heat. All right, so we're gonna do how many joules of heat are needed to raise the temp of 50.0 grams of iron from 10.0 degrees C to 30.0 degrees C. And the specific heat of iron is 0.45 joules per gram degree C. Okay. So how many joules of heat are needed to raise the temperature of 50 grams of iron from 10 degrees Celsius to 30 degrees Celsius? And you have the specific heat, and I'm sorry, I don't know why that's K. It should say joule. Let me give you all about 4 or 5 minutes to set that problem up and solve for it. Okay. So for this first one here, how many joules of heat are needed to raise the temperature of 50 grams of iron from 10 degrees Celsius to 30 degrees Celsius? I mean, it gives us a specific heat of iron. If you're working on a problem and it doesn't give you the specific heat, you can always like reference an appendix. But we're solving for Q. So I know that I want to find Q, and I know Q equals my mass. So I find, where's mass? There's mass. All right, 50.0 grams, and it needs to be in whatever the specific heat units are. So if this is grams, this needs to be grams. My specific heat for iron is 0.45 joules per gram degree Celsius. And then my change in temperature is going to be final minus initial. So 30 minus 10 is going to be a change in 20.0 degrees Celsius. You can see gram cancels with gram and Celsius cancels with Celsius. So we're left with just units of joules. In this case, we plug this into our calculator, and we round it out, we should end up with 450 joules. I want you to do one more. I'm only going to give you like 2-3 minutes for the second one. Let's say the temperature of 251 grams of water in a calorimeter is changed from 25 degrees Celsius to 30 degrees Celsius. How much heat did the water gain? Period in there as well. All right, so for this one, Similar setup. We're just going to be talking about water instead. So we're still going to use Q equals MC delta T. Our Q is what we're solving for. Our M is the mass, so 251 grams of water. Our C, because we're talking about water, is that 4.18 joules, it keeps doing that, per gram degree C. And then our change in temperature is 30 minus 25, which is going to be the 5.0 degrees Celsius. Celsius will cancel, grams will cancel, and we should be left with a value of Q equal to 5,300 joules. Does anyone have any questions on that, on Q equals MCAT and using that equation? Where our numbers came from, why certain units canceled, anything?
I have a question.
Yeah.
Do you just round it? Why did you round the joules at the bottom?
We always want to round to the lowest number of significant figures. So when looking at this problem here, 3 sig figs, 3 sig figs, 2 sig figs. So I rounded it to 2 significant figures. Same thing, excuse me. Same thing up here, 3 sig figs, 3 sig figs, 2 sig figs. So I rounded it to 2 sig figs. Make sense? Whoever asked, I don't know who was asking. Yes, no? Okay, well, I'm gonna, yeah. Okay, cool. Yeah, so if you're ever like, why did she round it to that? I'm just looking at the given information and going off of that. So let's go back over to the slides here. So we can run what's known as a bomb calorimetry. So we have this, we call it a sealed bomb. And what happens is we've got, it's pretty much what we've already talked about, but we've got a cup that's holding some sort of sample. We run an electrical current or we combust it to make it react, and it will release heat into the surrounding environment, which is water. The water has there's a little turbine here that's spinning the water so that we can evenly mix it. And then there's a thermometer measuring the temperature of the water. So as the temperature of the water goes up, it means heat is moving from this little cup sample out into the water. And because the volume in the bomb calorimeter, so this here is constant, we can assume that we're just measuring its change in internal energy and not its delta H, that those two things are equivalent. Or there'll be a very small difference. So let's see. This is where I want to go next. So I'm going to just draw a little picture over here to help out. So we've got our calorimeter, which is, you know, just a styrofoam cup pretty much. And well, we're going to make that. We're actually going to fill that completely with water. Okay. So it's got a bunch of water. And let's say that I have a piece of metal that I'm going to drop into here. And this metal is hot. Okay. Energy is going to flow from the hot metal out into the cooler water. The water will gather a certain amount of energy. That certain amount of energy that the water gathers is going to be equal and opposite of the energy that the metal lost. So we can say here that energy is transferred from the metal to the water, all right? Or the Q of the H2O, the heat of the water, is going to be equal to the negative Q of the metal. So if I know how much energy the water absorbed, let's make that a little bit more of a Q, I know how much energy the metal lost. It'll just be the opposite value. So let's try, we'll take a look at the slide problem and then I'll give you guys another one. So if 11 grams of hot lead metal, which we said is at 100 degrees Celsius, is poured into a calorimeter containing 25 milliliters of water, that what is the specific heat of lead if the temperature of the water rises from 25 degrees Celsius to 26 degrees Celsius? So when doing this problem, you have more information about the water than you do about the metal or the lead. We're trying to figure out the specific heat of the metal. So we'll start with our water information, and here's a big equation that says the Q gained by the water is equal to the negative Q lost by the lead. They've put it all into one thing here. We can just start with this if we want to. So we know that the heat gained by the water, Q, is going to be equal to MCAT, right? So this equals MC delta T. Now the mass of the water is, we don't have the mass of the water, but we do have the volume. We have 25.0 milliliters, but water has a density of 1 milliliter, 1 gram per milliliter. So I know that that is the same thing as its grams. So my mass for this thing is going to be 25.0 grams. My specific heat of water is always going to be 4.184 joules. And then the change in temperature of the water was 25 to 26. So final minus initial, or 1 degree Celsius is the change there. So my Q value, or how much energy the water actually gained, is equal to our 4.184 times 25 times the 1. We get 104.6 joules. Okay, so that's this number right here. Now, in order to find the specific heat of the lead, well, specific heat of the lead is going to be C is equal to Q over M times delta T. Q is the heat of the metal, and we can figure out really quickly the heat of the metal because we know the heat gained by the water is equal to the heat lost by the water. So the Q value should be negative 104.6 joules. Our mass of the lead, we do have somewhere, yeah, 11 grams. We have 11.00 grams of our lead. And our change in temperature is final minus initial. So the final temperature, it doesn't specifically say that the final temperature is 26, but it says the final temperature of the water is 26. So we can assume the water and the metal have both come to equilibrium at that final temperature. Okay, so we can use the 26 degrees for both the water's final temperature and the metals. So I'm going to take 26 minus 100, and it's going to give me a negative 74. The negative number is okay because this value is negative as well. So we've got two negative values that will then cancel each other out. The same thing is happening here. They're just combining it all into one step. I've broken it up here into step 1 and then into step 2.
Ask
Then
a
we
question.
yeah, what's up?
What's with the 100 degrees Celsius about the hot lead? Does that just not matter in that equation, or?
It was put in right here. So the changing temperature of the lead was
Oh, you did, okay. I missed that, okay.
-74. Yeah.
Okay.
Sorry, it's so messy here. We'll do one on the other page so it's be a little cleaner. So when we plug all of that in, so the negative 104.6 divided by 11 grams and then divided by 74, we should end up with a value of 0.13, and the units on it are joules per gram degree Celsius, because none of those units will cancel out. Okay, so we carry them all over. So we go from the information of the water to get the information about the metal.
I'm struggling to hear you right now. You sound very like echoey
Do I still sound echoey?
to me. I don't know if anybody else is getting that.
Yeah.
No, we didn't
Yeah.
need.
Okay, let me try something. That looks good. Any better? No. Yes. Better.
It's the same.
It's the same. Okay. Let's just log out and then log back in like 1 minute. Okay. I'm going to end the meeting and then we'll just log back in because that seems to really be the only way I'm ever able to get this to clear up. All right. I'll see you guys back in a minute.